Hello everyone, myself Sahil Gaurav, a PhD student at IIT Guwahati, here to present my paper. Virtual Oscillator Control of Series Connected PV Powered Converters for MV Grid Integration. The co-authors of paper are Hitesh Malvi, Somnath Maikap, and Professor Chandan Kumar. Now, first starting from the history of solar PV inverter, of course, it started with power lower voltage and the first came at mid 1970s. At that time, the IGBT and MOSFET switches have not developed, so the inverters are available of two types: line commutated inverters and self or force commutated inverters. These are based on the thyristor switches. With the evolution of power tonic switches, these PV inverters are being developed, and then they have been classified into three types: central inverter type, a string, and multi-string inverter types. Central inverter type is of less MPPT efficiency, but it is easy to use because of its high rated output, easy maintenance, and high reliability. In a string and multi-string inverter type, a string differs in many aspects, such as the rated output of module and inverter and MPP range. This string and multi-string inverter have more MPPT efficiency, and this multi-string inverter type has wide MPP range possibility with the use of DC-DC converter. Conventionally, for integrating the low voltage solar PV to the MV grid, decentralized PV converters are commonly used, and decentralized PV converters are used for range more than 5 kilowatt. The advantage of centralized PV converters are low maintenance costs and high reliability. However, fault or breakdown can hurt the entire system or causing significant drops in the solar generation due to single MPPT control. Now, for PV plants over more than 500 kilowatt, these multi-central converter technologies are preferred. The conventional centralized structure shown in figure number 2. And here you can see that enabling this large capacity PV power delivery through parallel connection of large center converters. So each module, you can say that this one is centralized PV converters, and if you connect all this in parallel, that enables the that enables large large PV power delivery through this central through power delivery to the MB grid. In multi-central types, here there are different types of multi-central PV inverters. In among these multi-central types, multi-banding transformer structure is preferred due to safety, low cost, and weight, and overall system efficiency improvement. And this multi-banding transformer structure is shown in figure number B and in figure C. In 3B and 3C, this multi-banding structure transformer structure is shown over here, and this efficiency improves in this multi-banding transformer structure for multi-central converter technology uh, due to isolation being provided in PV inverters that leads to minimization of common mode current. That also means that minimize the leakage current flow in through these PV inverters. If you see in figure number 3, there are different types of multi-central PV inverters with an MV transformer. This first figure shows with its own built-in low voltage transformer and two banding MV transformer. So each centralized converter has its own built low voltage transformer and then a two banding MV transformer. And in figure B, this is transformerless structure with a three banding MV transformer, and this is more preferred. And so this figure B and figure C structure is more preferred. And in figure C, this transformerless inverter with a four banding MV transformer. And this figure D, this transformerless inverter with a two banding MV transformer. Now coming to this figure shows one of the form of leakage current occurrence in a multi-central transformerless PV converter with a two banding MV transformer. So one thing I want point here is that when the grounding of PV module is not essential, the use of multi-binding MV transformer is not desirable. Instead, connecting PV inverters to MV grid via two binding transformer is more reasonable. And here you can see in this figure 3, outputs inverters of transformerless inverters are connected because of modules parasitic capacitance, that is CST1, CS2, CST2 and CST3. For safety concerns, most PV systems have galvanic isolation either in the form of DC-DC boost converter or in the form of high frequency transformer on the AC output side or in the form of bulky low frequency transformer. Now, since the multi-central PV converter technology are restricted to voltage and power levels due to two-level converter, so multi-central converters are introduced to achieve more voltage and power levels. And in order to achieve this more voltage power levels, multi-central converters have been selected to replace this two-level converter. And in multi-center converters, this first the neutral point clamp converter came, and it became popular due to its simple design, but its common DC link reduces the MPPT efficiency. Moreover, the transformer-less PV converter face challenges like leakage currents and DC current injection, which can exceed 300 milliampere at medium voltages, increasing electric shock risk. Multi-level converters such as CHV and MMC are required to achieve modality, higher efficiency, power density, voltage and power levels. And modular cascaded converters are nowadays used to facilitate the integration of large scale low voltage DC resources. If we talk about the control of CHP converters, the existing controllers rely on centralized and distributed methods. Although the centralized controllers are simple in design, but the complications happen with the increase in number of power modules due to the limited number of ADC channels and PWM on a given digital control platform. In order to overcome these limitations, we proposed a fully decentralized control comprises of arbitrary number of test bridges with communication-free synchronization. The decentralized control is based on the AHO-based VO control. It is time domain-based controller that has similar dynamic response, including that includes real and active power set points, global asymptotic stable, and that mitigates low order harmonics. This table one shows the comparison of different decentralized grid forming controller strategy, where this Droop and VSG comes on the synchronous database, while in oscillator base, the commonly used controller strategy are VDPO, the Van der Pol oscillator, then dead zone oscillator, and then Andronov-Hopf oscillators that has been used here because of its several advantage over the other oscillator based control strategies. This figure 6 shows this cascaded H bridge converter module with nonlinear AHO based VO controller. Now coming to the AHO dynamics, where you can see this AHO dynamics expressed in the form of state variables, where this x1 and x2 are state variables, and these are nothing but these are state variables are voltage across capacitor and the scaled inductor current, and this orthogonal signals are used to generate the PWM pulses, and these we can use for the alpha beta signals, and then alpha beta signals are being transformed into ABC signal, and that is this modulating signal, and modulating signal given to the PWM generator, which ultimately provides the gate pulses for the converter. And for this oscillator dynamics, we have characteristic impedance given by under root of L upon C, where L is this virtual inductor and C this virtual capacitor, while nominal solution frequency is defined as under root 1 upon LC, and this nominal frequency is equal to the rated grid frequency. Now let us come to the AC side dynamics. If you select this rotating angle phi equal to 0, uh, then this steady state voltage frequency dynamics comes, where this angular frequency depends upon this reactive power mismatch, while voltage voltage magnitude depends upon this active power mismatch. And if you select this rotating angle equal to pi by 2, this uh, dependence of this angular frequency and this voltage inverses accordingly. So for this reactive power versus reactive power and this this angular frequency relation, that do not depend upon just like a group control. This also depends upon this voltage magnitude. So we have a three D plot for reactive power voltage frequency curve. And now for this voltage and active power relations, here you can see this is a non-linear relation, and that comes certainly from this non-linear oscillator dynamics. And this is given by this figure number 9, where we have shown this real power voltage PV curve, and that denotes the nonlinearity comes due to the nonlinear oscillator dynamics. And now this amplitude and angle of each set of this AC terminals are controlled by separate VO control, and that if we sum up, then that equal to the voltage MV voltage grid. And this active and reactive power flow through each converter module is given by this equation. And this figure 10 shows this AC side phasor model consists of n series cascaded bridge modules across the grid and line filter. Now let us see the simulation results, where this we have shown this active reactive power output each module in the figure 11. As of now, we have done this simulation for all these H bridge modules set it as equal reference power. So we are seeing this power output coming from the each module is overlapping to each others. And if we change the reference power to the module, then we have to see its stability point of view. As of now, we have set the reference power to all the modules equal. And here you can see this initially this active and active power difference are set for the modules at 0, and at t equal to 1.5 second the active power reference is changed to 4 kilowatt, and t equal to 5 second it is changed to 8 kilowatt. The zoomed waveform is taken at the moment of power reference changes as indicated by the dashed box, this one. And the voltage remains stable and synchronized during changes in power reference set points as shown in figure 12a. And the converter reacts quickly to change in power references as given by this figure 12b. The enlarged view of voltage and current waveforms are shown over in figure 12c and d, that illustrates the quality of power being injected into the grid. And each module regains its synchronism after experiencing disturbances. The steady state frequency of each bit module is maintained at 50 Hz. Now at the last, let us see, coming to this conclusion of paper. Here this paper proposes a decentralized control technique to synchronize and control multiple number of series connected three-phase PV power converters supplying power to the grid. The proposed time domain based control technique differs considerably from the conventional phasor domain based methods, and this control technique facilitates voltage synchronization and power sharing among the cascaded HV modules without requiring communication. The active power delivered by a specific module which can be adjusted based on the available PV power, and the simulation result is shown to show the effectiveness of proposed control strategy and its fast transient response. That's all. Thank you for your kind attention. If you have further queries, kindly contact to this email ID sahelgaurav@iitg.ac.in. Thank you.